Okay, let's dive into this. We've all seen those amazing videos of robots, building cars with incredible precision or even helping out in surgery. But have you ever really stopped to think about how they actually do it? Because at their core, robots face this huge fundamental challenge. They just don't think like we do. We think in bowls, right? Like draw a square or pick up that cup. A robot, it only understands one thing: how much to turn its motors. So how in the world do we bridge that gap? Well, it's a fascinating puzzle. And today, we're going to solve it together. This right here, this is the central question for our whole explainer. We want to command this simple robot arm to trace out a perfect square. But here's the catch. We can't just tell it, move up or move left. Nope, we can only send it a list of angles for its joints. And yeah, that sounds like a massive translation problem. And spoiler alert, it is. But trust me, by the end of this, you'll see exactly how it's done. So to even start solving this, we first have to get our heads around the idea that we're dealing with two completely different worlds. You see, the robot lives in one world, and we live in another. The entire science of robot motion control is really just about building a solid bridge between them. On one side, you've got what's called joint space. This is the robot's world. It's all about angles, theta 1, theta 2, and so on for each motor. It is literally the only language the hardware understands. And then on the other side, you've got task space. That's our world. It's defined by good old Cartesian coordinates, the XY position of the robot's hand. Our goal, draw a square. That's a task space command. So the whole game is about creating a perfect translator between these two languages. All right, so the first part of our translator is something called forward kinematics, or FK for short. Now, this is the more intuitive direction. You can think of it like a map that lets us go from the robot's world of joint angles over to our world of coordinates. And it all starts by answering a very simple question. And that question is simply this: if I tell you the exact angle of every single joint on this robot, can you tell me the exact XY position of its hand? And the answer is, of course you can. And what's really cool is that for a simple two-link arm like this one, the math is surprisingly straightforward. We don't need any super advanced math here. Seriously, this is just some basic high school trigonometry. First, you calculate the position of that first elbow joint using its length and its angle. Then, you just pretend that point is your new center of the universe, and you calculate where the second link ends up. Add those two pieces together, and bam, you've got the precise location of the robot's hand. And check this out. What's so wild about this slide is that last column, the error column. This isn't some approximation. Our simple geometric math gives the exact same result as a super high-fidelity physics simulator, right down to the micron. Zero error. So, okay, for any set of angles, we know exactly where the hand is. We've solved the static map. But hold on. Drawing a square isn't about teleporting to four corners. It's about the smooth motion between them. So how do we map not just position, but speed? And this brings us to our second and honestly unbelievably powerful tool, the Jacobian. If forward kinematics is the map for position, the Jacobian is the map for velocity. It's the tool that tells us how the speed of the motors translates into the speed of the hand. And believe me, this is where things get really cool. Now, I know, that definition sounds super intimidating, right? A matrix of partial derivatives, what? But the core idea is actually brilliant. So here's the key aha moment. Just think of the Jacobian as a dynamic gearbox for the robot arm. You tell it how fast each motor is spinning, and it tells you exactly how fast and in what direction the hand is moving. It's like the instantaneous transmission ratio between the robot's world and ours. And this beautiful, elegant little equation says it all. X dot on the left, that's just a fancy way to say the velocity of the hand. Q dot on the right, that's the velocity of the joints, how fast the motors are spinning. And that J in the middle is the Jacobian matrix that connects them. The really crucial part to get is that this J matrix isn't constant. It changes depending on the robot's current pose, so our gearbox has a constantly changing ratio. So what's actually inside this matrix? Well, each of these elements just answers a pretty simple question. For example, that top left one just asks, if I nudge the first motor just a tiny, tiny bit, how much does the hand's X position change? By calculating this for both joints and for both directions, X and Y, we build our complete instantaneous velocity map. Okay, we have our toolkit. We can go from angles to position with FK, and we can go from joint speeds to hand speed with the Jacobian. Now, we are finally ready to tackle the main event, the problem we actually need to solve to control this thing: going backwards. This is it.
This is the whole enchilada. This is the inverse problem, or what everyone calls inverse kinematics, IK for short. Given a target coordinate in our world, a specific XY point, what are the motor angles in the robot's world that are required to get there? This is the core challenge.
And let me tell you, it is not easy. Unlike forward kinematics, which is pretty straightforward, the inverse is, well, it's tricky. For a single target point, there can be multiple right answers. You can try this yourself, right? Reach for something in front of you with your elbow up and then with your elbow down. Same hand position, different joint angles. Or the target might be too far away, giving you no solution at all. And sometimes, in certain poses, like when the arm is stretched out perfectly straight, the math can just kind of break down. This is where the real robotics magic happens.
So, with our full toolkit, we've got forward kinematics, the Jacobian, and a way to solve inverse kinematics, we can finally execute our plan. Let's see how all these pieces build into a complete control pipeline to draw that perfect square. So here's how it works, in 4 steps. First, we plan a smooth path for the hand in our task space. Just defining the square's corners. Easy enough. Second, for every single tiny point along that path, we use inverse kinematics to find the required joint angles. Third, we use the inverse of our Jacobian to figure out the necessary joint speeds to move along the path. And finally, here's the secret sauce. A smart controller uses a model of the arm to calculate the exact motor forces needed to counteract gravity and inertia and follow that path perfectly. It's like a cruise control system for the robot's arm, but way, way smarter. So, after all that math, the planning, the IK, the Jacobian, the fancy control, what's the result? How well did it do? Well, the average tracking error between the perfect square we wanted and the one the robot actually drew was this, 0.008 of a millimeter. To put that in perspective, that is less than the width of a single human hair. Just incredible precision, all achieved by translating our goal from our world into the robot's. And that really brings us to the final, much bigger question. This was never just about drawing squares, right? These exact same principles are what allow robots to assemble our smartphones, 3D print houses, and assist in delicate surgery. So the real question is, now that we have the tools to translate human intent into machine action with this kind of mind-boggling fidelity, what are the next great challenges we should teach them to solve?